Okay. I should be live now. Welcome, everybody. This is the first live stream I'm doing. First of all, sorry that I don't have a webcam at the moment. I was trying to set it up, but couldn't get it to sync properly, and this was more distracting than helpful. I will keep working on that. So we are going to be writing a C compiler, or rather a C interpreter in this live stream today. We're not trying to implement like the entire subset of C23. Obviously, we're just picking an interesting subset, see how it goes, and how long, essentially until we get bored. The idea is to essentially try out Lauf, which is an interpreter library I've been using. I'm just seeing how it goes. So to keep this project more manageable, we are essentially assuming that the user gives us well-formed input, so we don't invest a lot of time in generating good error messages. We are only testing the happy path and so on. We also don't try to implement an existing C API, so this consists of things like the size of the built-in types and how they're passed to arguments. The C standard leaves a lot of this implementation defined, which we leverage to essentially make our implementation as easy as possible. We will also not try to implement the C preprocessor for now. We're simply assuming that the user's already preprocessed the file for us. It's just a parsing exercise that isn't too interesting. What we are trying to do is to turn as much undefined barrier into runtime panics as possible. So this includes like integer overflows, but also invalid pointers. Lauf has pretty good sandboxing that we are excited to try out. Okay, let me see the comments. It's also 720p as well. I will keep working on that as well. But it should be, you should be able to read the code. Let me know if that's an issue otherwise. Okay, I've already created, the repository is linked in the description. I've already created like a basic outline. This is just simply a main function that sets up some command line arguments. It hasn't implemented anything right now. And the goal for this stream is to get this simple test file, empty main, to get this to compile, parse, and execute. So this should just return 0. Okay, so let's get started. Here in the setup, we need to do essentially like 3 things. So the first thing is we're already reading the file. This uses lexc, my parsing library. So we're reading the input file, and then we need to compile it into the AST. And this is the first step. So let's define the AST first. Let me actually rename that to s.hpp. Okay, so the AST is the core compiler data structure. It's a tree because a program lends itself to a tree form pretty easily. For example, when we have things like expression like 5 plus x, this can be passed into like an add expression, which is like some sort of node in the AST, and which has 2 children. The first one is an int literal, which is the number 5, and the second one is the name, which is x. And so this is a tree data structure, and there are essentially 2 ways of implementing that. The first is to use inheritance. Like we have an expression-based class, and then we have add expressions and literals and names, and they're all subclasses of that. And the second is because we know that all the potential subclasses up front, we can use unions or variants. The issue there is that because, for example, an add expression can be itself, one of the children can be another add expression, so we have recursion in there, which means we can't use variant directly, we need to use heap allocation. I've blogged about that recently. This isn't not, in fact, the route we're going down here. Instead, we're using the inheritance-based approach, but with a couple of optimizations. The issue with the inheritance approach is, for example, what we need to do is to allocate each individual object. And this can be quite expensive and lead to memory fragmentation. So the idea is instead to use a big arena and then allocate individual parts of that arena. The second issue is that when we want to traverse the AST, this usually involves recursion. So we visit the add expression, and then we visit the left child and then the right child, and this calls itself recursively, which can lead to stack overflow. So instead, a better way would be to have each node intelligently have like pointers to the next one in traversal order, then we can just follow all the pointers. We can also conveniently filter them based on what sort of node it is, using that approach. And finally, what we might want to do, for example, if X is a long, we need to promote the 5 to a long as well. So we might need to conveniently provide a way to like have an implicit conversion node here. So like formatting that to adjust the children and so on. And this is where a library I've been working on comes in. In fact, I've started this library on Sunday. It's called Riot. It's like some Greek thing for trees or something. And it essentially provides like convenient ways to create ASTs. This is highly experimental. We probably have to fix a lot of bugs while we're doing that. So let's just see how it goes. Let me also add this to the CMake list, so we're getting proper error messages. Let me restart the IDE. Okay, now it works. Okay, so the first thing that we need to do is define like a big enumeration of all the different nodes in our class, in our SD. So the node count. Yeah, I have a pretty fancy Vim setup. It's all in NeoVim, but I have FZF integration and language server. It's a bunch of Vim script code, like 2,000 lines or something. I spent way too much time on it, but yeah, it's pretty cool. Okay, so what sort of nodes do we have? First of all, we have like the root node, which is a translation unit. This is the entire root thing. What we pass out, we get a translation unit. And then in our case, so we start out quite small. So we have a function, right? That's the first kind. So we've got a function. Let's call this declaration function decker. Okay. And then a function has like a bunch of stuff, but for now, the only thing it really has is a type. So a function has like a type. In this case, the type is it returns int and takes no arguments. So we also need, so this is like a bunch of declarations in here. And then we have types. Let me put those first. So the first type is a built-in type. So int is a built-in type. And then we have a function type. So this is the type of our function. And to prepare stuff, you also do things like first type. It's built-in type, and last type is function type. And likewise, you're doing first type. Okay. So let's define the actual data. Start with the types. So now we define a base class for all the types. I don't actually need to know whether we need any data for that. First of all, let's define the base class for all types. So this is a node in the AST is simply a derived node with our node count. And now you're complaining again that you let me include this one here to see how the okay, now this works. So this is just the base class. It defines a bunch of useful functions. For example, we can get the parent of every node. We can iterate over the siblings, over its children, and so on. So this is just a bunch of convenient functions. And then we define a type. This is an abstract node. We should include abstract node for that. This is like a base class. It's in turn inherits from base, and we have the first type, last type, and then I need object node range. So let's see type. Okay, so this is the base class for all. We can then inject, whenever we need like some data common for all types, we can put that here. We don't need anything at the moment. We need to define the constructor as well. Okay, so first type is built-in type. How do I best? So a built-in type is a node of type built-in type, and it inherits from type. So this is now a concrete top-level type. And then we go ahead and actually make this class. So we've got various kinds of built-in types, so we need some kind of enum here as well. And for now we just have it. It's annoying that you can't name things like keywords, right? This is, but anyways. And then we expose the type kind. Yeah. And this is UN60. Okay. And then I need a semicolon. Okay, so a built-in type can be multiple types. Currently, we're only having int, and then all the data the node remembers is like what kind of built-in type it is. And we're using this macro to conveniently inject that into the base class, because the node base class has a bunch of padding, and we can expose that way, so we don't need to add additional space. Like there are 16 bits of padding in the base class anyway, and we just repurpose them to store the built-in type. Finally, we have a function type. This is also a basic node. And okay, so this is a function type, and the function type currently, it has a child, which is the return type. So, like for example, we've got the function type int this type has multiple children, like the return type, which is an int, and then it has arguments short and long, and those would be then the built-in types as well. For now, we don't have arguments, so don't worry about those just yet. Just have a return type, which means that every type potentially has child types. So we need to adjust that here by inheriting not from node, but from the right container node of node. This then makes it tells the right that we might have children node, child nodes in our types. So now we can define the return type. So let's just say that you always have to pass the return type in the constructor. So the constructor of function type needs to take this key, this is a dry thing, and then we also take in our return type. We're passing that to the node base. What's it called? Node base. Node base constructor. And then we say that the first child is our return type. And then we provide an access for that. For that, we get the first child from our base class, the children front, and then we do a downcast to type. Okay, and now we get the return type of our function type. Let's actually do the same thing over here. So let's make the attribute private and have the constructor set it. Rename that and expose this again here. Okay, so now we can do that. This should conclude all the types. And finally, we have the declarations. See now, looks the same way. We define a base class. We call it decal. It's also a container type. It ranges from the first decal to the last decal, and it has an abstract node constructor for decal. Okay, every declaration has a type and a name. This isn't quite true for C. There are things like static assert, but for now, let's just say that every declaration has a type and a name. So the name is a string, but we want to do efficient comparison of strings, so we need string internal. That way we only have, like, compare the pointers directly, because unique strings, if we have the same string multiple times, they will all have the same address. For that, we can use write again and also define string internaling. It's almost as if I thought this one through. So try at the symbol. And we define an ID, so s symbol, which is just the type, and then we can say that an s symbol is just symbol for that ID. And let's do a premature optimization and say that we don't need more than 4 gigabytes of string data. So now, this one's actually a protected constructor. I'm pretty sure I have user data, so I also have 32 bits of data I can repurpose. Yeah. So we again use padding bits for the string. For there to store the actual name, so we store an s symbol. Let's just allow the user to rename it. So let's just make it public. Oh, right. I can't, I have to do this one manually. So, name. This constructor is actually private. Okay, let's do that later. This is something I need to fix in Riot, so let's just do it here. I don't have this is constant. Okay. Why do you prefer a single node class for all built-in types with an enum to discriminate them over a node class for each built-in type separately? So this is essentially the same thing. The advantage is that we often need to uniformly treat all built-in types the same. For example, a simple would be to query whether something is a built-in type. Then we can just say if it has the type built-in node type, then it is built-in. Otherwise, we need to manually check a bunch of different types. But this doesn't really matter, especially for we will for a long while only have int anyway, so it absolutely doesn't matter. Okay, so a declar has a name, a declar also has a type. The type again is the first child. So when we visit a declaration, we will then go to the first child as its type. Just because why not? So we've got the type. Let's do the same thing here. Why are you complaining? Oh, because we need to reconstruct. And C is a great length. Do that likes it. And then also set type. Let's don't do that for now. So let's just say that the type must be passed in the constructor. As long so a type, and this is mutable. Passed in the constructor, not base. And the name is the first child. No, you're not unused. Okay, so this is the base class for all declarations. And finally, let's define a function declaration. This is again a basic node. And it has come back. Okay. That's all the relevant. Finally, we just need the root node. This is the annoying bug that something causes the language server to crash occasionally and then have to restart Vim. Okay, so translation units. Basic node, node kind. Translation unit, and this is also a container node. This is an abstract constructor translation unit. And constellation unit basically contains a bunch of declarations as children. So we just have declarations here. So we can have a function that takes a declar and simply call. I don't need this here, insert child after. Is my language server dead again? So when we add the declaration, we simply add it to the font. This means that they will all be stored in reverse order than actually defined in the source file. But since we are resolving all, this doesn't affect name lookup, it doesn't matter and simply easier to do because we have a singly linked list of children, so we just add them to the font because that's easier to do. So this is the C source file. Okay, and then finally the AST. is then simply a dry tree for our node kite, where the root node is always a translation unit. Okay. Let's try this out by manually build the AST. So we first need to construct in the interface. So we create a tree. We first get a translation unit. Translation unit doesn't take any arguments, and mark this as the root node of our tree. Finally, then we actually need a function type. So we first need an int. So great, built-in type int, and then the type of main, which is function type. Do I have the ability to set? I don't have the ability. I specify the return type here. No, this is the function type. Specify the return type in the constructor. So int type, and then main. It's a function decker. The name is, so for that we also need a string returner. For ast symbol ID, 32-bit symbols, into main and main type. Why don't you like that one? Oh, this has different arguments. So here the arguments actually are Java. Okay. And then so this is now, we've manually created our ST, and we can now dump this by simply traversing the entire tree. So let's use the visit interface. So do I provide the function visit? We want to visit all kinds of nodes of our entire translation unit. And then we do the following. When we see a declaration, let's say when we see a declaration, we do function declaration, and we simply print out its name. Okay, and now when we run it, we have a warning. Oh, right, because we actually need to go ahead and add main to our team. This were the tests. We've got the output here. Right, this main is what we printed. So we created the function manually by hand. Let's actually implement a proper stamp now. Because we will always need access to the symbols, let's just turn the AST into a struct that contains, let's just call it, I don't know, how do I call this? Yeah, 3, and I add symbol internal as symbol ID char to symbols. And then just write a function dump AST. The boilerplate is so annoying. Okay. So what we want to do is we want to visit every single node in this tree. And then we essentially write a lambda for each type that we have. So, translation units. That's about the visit event. Traverse event. For translation unit, it's simply just only the children matter. The unit itself doesn't, so we do not print anything. In fact, then I don't think we have it. Next up, we are having types. Because we also need to, like, when we print the tree, we need to indent it dynamically, so let me just add the boilerplate that for level is 1. Okay, so indent, and then we switch our built-in type kind. Puts as a new line. Okay, and when I so visit versus visit all, the visit all just asserted that we handled every type, which means if we remove that and go back to our main, we're here. We need to adjust some things. What the hell? No matching curve, const love seeker into traverse range. Why? What's exactly is here? This is the downside when you use library you wrote over the weekend. So you want a t pointer. Oh, we're missing a const here. And then we're also missing a const here. Now this one is private because we're missing a const here. Isn't C++ fun? And now we are doing... Wait, why are we missing a const? Why are you trying to cast away constness? You shouldn't be. It never works, obviously. Oh, because we're decaying it earlier. So this is the code. It's really smart. It looks at the lambdas, looks at all the argument types, and tries to figure out whether or not we can want to call that lambda. But it let me just use this C type here until I fix this one properly off screen. Because I'm decaying the argument type, it doesn't really like them. And now I've messed this up. Okay, and now here we're printing the AST. We're only printing the int, because that is what all we did. But this part works. We need to cast away constants in a couple of places, but yeah. This is what you do. I will fix the dry part later. So then we also have function types. There we don't actually need to do anything there, because they simply, like, we would just want to print all the children, and then we know the first child is the return type, and that's it. So we don't need to print anything itself except handle like the indentation. So for that we can look at the traverse event. If this is if we're entering it for the first time, then we need to indent it, and I guess we need to print like this is function type. And then increment the level for all the children. Otherwise, we are decrementing the level. And this is correct. We don't need this one. And now we're printing with a function type, and the return type is it. So these are all the types. Let me add a fancy comment here as well. Types and declarations. So for declaration, we just essentially we can uniformly currently just treat them all the same. There again need the traverse event, because all we need to do is, like, we want to print its name and all its children, regardless of type. So if we're entering it for the first time, we essentially copy this code over. I guess we want to do, yeah, let's only having one anyway. So we want to do like this is a function, and its name is C string symbols. And now when we print them, we get the proper st. So the function name, its only child is its type, which is a function type, which returns it. That should be, like, we can obviously make that fancier, but I would call this one done for now. So now we can assert that we're visiting every node, and we can remove that to do. Okay. Obviously, we don't want to keep building the tree manually, so let's actually write the compiler. So the job of the compiler is to take a buffer from Lexi and convert that into an AST or an error. So if the input is well-formed C, including name, lookup, and type checking, return its AST, otherwise log error and return nothing. Now, the reason is, like a traditional compiler, you would have like a parser, and then you do like name lookup, and then you do type checking. But C has been designed pretty efficiently to do like a single pass compilation, so we can essentially do everything in one go. Because name lookup, for example, can only refer to names that have been declared before the file. So we can do everything in a single, in one go, and just get the fully the one as at the end. This makes the implementation a bit easier. So let's do the other relevant boilerplates. We need a CPP file. We're probably going to split that into multiple ones in the future, but not for now. We also need the AST. And add this one over here. Okay, so the first thing, parse the input. Oh, well, it's not the first thing, it's interleaved. So for parsing, we're using Lexi, which is a library I wrote. So we define the grammar in some sort of DSL. We also want callbacks, and we want to parse things. Let me actually go ahead and write the function in here. And call it for main, just so that we have st equal to compile file.buffer. Not as we had an error bitte. And then we need to include the compiler. Wait, why do you? Okay, so this, yeah, done. Okay, so the grammar. We first need to define like some sort of basic lexical properties of C files. For example, the white space. It's just ASCII space. ASCII space, and I said that we will only look at input that has already been preprocessed. However, for convenience, we will allow comments in there as well, so we can just write them in our text. So let's support comments. This is either 2 slashes until we reach a new line, or C-style comment and again, C is very convenient because the C-style comments, they don't support nesting, so we can just say stop when we reach the next one. Otherwise, it would be a bit more complicated. Then we also have identifiers. So identifiers, this is one of the reasons we are actually looking at C23. Identifiers have become Unicode aware. So they're using this XID stat, which is a Unicode property. They're also using stuff like universal character names, but we're not supporting those. So this means that an identifier now is a proper Unicode thing, where we've got XID start or underscore, because non-digit, yeah, underscore, which isn't normally part of Unicode property. XID continue. I'm assuming continue allows underscore, since I have XID continue underscore. Okay, so this is an identifier. And then we also have a bunch of keywords. So the first one is int. Okay. So the proper grammar for declarations in C is a bit complicated. First of all, the formatting is a bit broken because this is an early draft. But it has this, because like C allows stuff like this declaration declares a pointer to int called f, a function that returns a pointer to int called g that takes a single argument of type int, and an array of 42 int pointers. And this is like really messy. So we will slowly work our way there, which means that for now we will just essentially parse like a simplified grammar and then extend it how much is necessary. So let's define our types first. I like doing this nested namespace thing. So a type. We've got the built-in type. And a built-in type is simply a mapping. We've got a mapping that returns what's it called? Zero built-in type kind t, and then we map do I not allow, this might be an error, and this is zero built-in type int. Yeah, and this is an error, so we need to do this one a bit different. By defining the mapping entropy. Okay, so a built-in type simply parses then a built-in symbol. So it passes a symbol from our built-in table. And then it produces as its value. As value, we want to make now a built-in node type. For that, we need access to like the tree structure so we can inherit it, which requires writing a parse state, or rather a compilation state. So the compiler state, it contains the AST that we're currently working on, and then let me write a utility function for here. So this is a thing I will explain later. Callback and just like so when we parse stuff in Lexi, we get all the values, and then we want to pass them to the callback, but we also want to inject the parse state, which is our compiler state. So we can modify that, and we also need to make this one mutable. So this means that this is now a callback. That is a Lexi callback, and that's annoying. Let me inline that as well. Callback. So this returns built-in type, and it takes lambda. The value that we've got is the zero built-in type kind, and then we've got the compiler state, and then we do state.ast.create a built-in type for our cat. Okay, so this compiles. Since we are doing this tree.create a lot, I don't know why this one keeps crashing. we're adding a convenience function right here. So just so we can make creation a little bit easier. And then we can, over here, we can just call create. Then we've got our function type, which we don't actually pass because it doesn't happen in our grammar at the moment. So we just have the return type. And then manually, when we do the function, we do that. And for now, let's just say that a type simply parses a built-in type. Let's move on to the grammar, the actual function declaration. So a function decl, and again, we will hard-code it and expand this one later as necessary. So we first pass the return type, then we pass a name. So a name is an identifier, but we want to reserve a literal set containing all our built-ins. So like those identifiers are reserved and must not appear as part of a name. And then the value, we have a callback that returns the C.S symbol, and this simply interns. Here we are getting like theme is what it's called. I'm having a bit of syntax issues here. Okay, so like theme, we will first, we're doing something really hacky here that we might fix later. So pointer, and then we return state as that symbol that intern pointer xc.length. So, and we don't have to get it. So the issue here is we are parsing UTF-8 encoded text, which gives us char 80s, but we don't want to deal with char 80, so we turn them back into char. This is actually not UB because char can alias anything, it's just not nice. So function declaration has a type, it has a name, and for now it has nothing, and let's make this an open paren, close paren, and the value is a callback that takes the state. We're returning a function decl node. We get return type and name, and then we return a new function decl using the function type and its name, and the function type is a new node for the function. So a function type where we specify the return type. And finally, we have a translation unit. And the translation unit, this is the top level production, so we also specify our whitespace rule, which is this whitespace. Let's just actually define that here. And the rule is simply a list of translations. So until we haven't reached the end of the file, we pass a list of declarations, which for now A decal is simply a function decal. And as its value, we are creating the root translation unit node. We actually need to, this is annoying. Let's just make our lives easier and temporarily put them all in a vector, and then we get a vector of decals create our translation unit, doesn't take any arguments, and then for auto the decals to add declaration d return t, and then I need vector. Okay, and this should compile, or it doesn't. Why do you not like this one? Oh, main vector. Which means that now we can go ahead and parse our inputs. So we first need to create the compiler state, then we parse the result, our input. This one actually don't really need to return anything, because we just specify that the root node is OTU, and then we are parsing a translation unit on our input using the parse state, using Lexi's default error reporting. If that failed, then we return. Otherwise, we return state.est. Need to include report error for that. This is extended. Get a bunch more errors. Conversion candidate. Oh. We're actually getting the const, which is why we needed the mutable. Okay. Hey, it actually compiled. And it works. Right? We're saying we want to compile the SD, and then we're dumping it, and this is the SD. Right, sorry. I've been just, yeah. So what we did so far, we've written a function that compiles this simple program. So it takes the buffer as input, and then parses the grammar that we defined in Lexi. The grammar right now is like pretty limited to what we're doing. So the root termination is a translation unit. This simply contains a list of productions. Actually, it might not. Yeah, let's worry about that later. Contains a list of productions. We will then translate them by simply creating each individual node, adding all the children to the translation unit, and setting it as the root node. A function declaration, again, this is what we are currently hard coding it. So consists of a return type, a name, and no arguments and no body. And once that is passed, we create a function type for that and add a function declaration. And for types, we are currently only having built-in type. So when we int, we create a built-in type of type int. Then we can dump that AST this simply iterates over them and does some printing magic, and the result can be seen here. So this means we can now compile this program. We can also add a comment, and comments don't show up because they're treated as white space. Okay, so the next step, we didn't have to worry about tokenizing exactly because Lexi doesn't have a separate tokenizer step. It simply does tokenization on the fly as necessary, and also does like white space skipping. So it's pretty smart about that. We didn't need tokenization. Yes. So let's now go ahead and continue on. The next step is to generate bytecode for our ST. For that, let's add a couple of new files. Let's call this Codegen. And this is where Lauf finally comes in. So this is a module. And the goal of Codegen is to take the AST and return a module that then contains our bytecode. Module is a keyword. Codegen, our AST. Okay, so let's generate Codegen. For that, we first create a module, a Lauf module. Let me directly. So we create a module. Let's just call it main module for now. Then we return that module. Now, again, we need to iterate over the AST, similar to dumping it, but instead of dumping it, we're creating individual actions. So this is currently, again, not the way it will finally look. But let's just copy. A translation unit itself doesn't have any Codegen. And also types don't need any Codegen, because the types themselves don't show up in the final code, especially because we don't have anything but int at the moment. Come to think of it, let's actually write separate functions for those. So let's write a function that codegens a function. A function declaration. So, and then we also need we probably need some Codegen states, not on this level. So we need the module. And then we say that simply we add a new, we do need state. Let's just call it context. This contains the module that we're currently compiling to. And there's a question in the chat, what does Codegen do? What we're generating is a lauf module, which is lauf as a library. A lauf module is essentially bytecode, which lauf can then execute. So we don't generate any assembly, we generate lauf bytecode, and this bytecode can then be executed by lauf's VM. So the context, we need the module, and we also need like the AST. So what we need to do is get the name of the function. We need to get the name, and then we simply add a new function in that module with that name and the signature. Let's hardcode the signature. So it returns, takes no argument, and returns 1. And then return the function. So this now adds a function declaration too. Let's actually see that. So here we go ahead and visit all the translation unit, on the children of the translation unit. Let's do that here next time. So when we have a function decl, we call Codegen function context decl. We don't actually need the return type at the value because we don't support calls. So we can just ignore that because nobody will ever refer to that function ever again. So the context is the mod, which order was it? The est, and then the model. Okay. This should compile. Except, okay. So now we are currently we're just generating a function declaration. We can see that by getting lauf to print to dump this stuff. Let's get log lauf back and dump lauf writer. So for that, we write the standard out, and then we dump the writer, dump options, the module. So what? Let's actually go ahead and add some labels here. So the bytecode currently contains a module, name is main module, and a function called main, which takes no argument and returns a single argument. But we don't have a body yet, because we haven't been generating a body. So let's go ahead and generate a body. Currently we have an empty body, because we've been hardcoding that. So all we need to do is simply return 0, because when you have a main function before the return statement, it automatically returns 0. This means that we need to create a builder. A builder builds the body of a lauf function. And creating a builder is quite expensive, because it needs to involve a whole bunch of heap allocation. So actually, we're going to store the builder in our context. Let's actually go ahead and give this one a constructor while we're at it. So we create the est, and then we store pointer to the est. We create the module. We create a builder. Default build options. Let's also give this one a destructor because we need to destroy the builder when we're done. We don't want to destroy the module because we're using that one. So now we get the builder. And we start building yeah, let's call it B as well. Start building the function in our module. And finally finish. Okay. So now we can build the body of our function. For that, we need to do two things. First of all, we need to return. Okay, no, that is wrong. First of all, we need to create a basic block. So the body of function in Lauf contains a list of basic blocks. And the basic blocks are like a sequence of control flow, a sequence of statements that are executed without control flow. So, for example, when we have a function like so, int x equals 42, return. The body of this function is one basic block. First we allocate x, then we set x to 42, and then we return. But if we do things like, now the function has multiple basic blocks. First we are allocating x and setting it to 42, and then depending on the value of x, we are either jumping to this basic block that just returns, or to this basic blocks that set it to 11 and returns. So each of those is a single basic block. Here we have an empty body, so we only have one basic block. So let's create this one. This is also the entry basic block. So we build. We don't build a block. We first declare the block. Declare block. Blocks also have signatures, which the entry block takes as input all the arguments to the function. We don't have any, and it produces, like, the output depends on the basic block that it calls at the end. Since this is our only one, we also need to have the return type match the function. So it takes no arguments and returns one value. Then we can start building that block. So we start building the entry block. And Lauf is a stack-based machine. So what we means is that we first need to push a value, and then we can modify it, and then we return it. So in this case, we want to return 0, so we need to push 0. So we push an unsigned integer, or signed, doesn't matter because it's not negative. So we push 0, which means that here the stack is empty, and here the stack contains 0. And once the stack contains 0, we can then call return, which returns from the function, returning everything that's currently on the stack, so the number 0. So when we adjust the code here at the bottom, that creates the context. What we should see is bytecode for a function. So our function main pushes 0, and then it returns. So this means that we're now ready to execute. To execute bytecode on the Lauf VM, we create one here. So we create a VM, and then we can't execute a module directly, so we can only execute a program. And a program can be multiple modules and an NP function. In this case, we're only having a single program, so program Lauf. I need to include a header here. Sim program, create program, contains our module and the main function. So the main function, find function by name, module, main. Then we create a program, So this program, can we start executing it, and it will start execute the main function. Then we call execute one shot on our VM, our program. We need to pass out the input value and space where we can write the output values. So we don't have any inputs, but we do have outputs. So the output value in this case is a web representation of values, return code. So the return code we can write in here, and this execution can fail. Then we simply return, because it will print an error, and otherwise return code as signed int Angular 0. Then we print an error. Program failed. Exit code. That's actually 64-bit, so we need the appropriate. Let's just cut the print, and then we return one as well, or whatever, and we can execute. And it prints nothing because it succeeded. This is a bit underwhelming. So let's just say here, let's just, yeah. Program succeeded. Which means we've now taken the input file, passed it into an AST, converted that into bytecode, and executed that bytecode. We can now also run the tests, and the tests passed. Good. There are a couple of issues. Yes, loaf is a stack machine, which is why we're dealing with push instructions. Like we're pushing a 0 and then we return. So let's commit that. Execute empty main function. Yes, somebody in the chat pointed out that we're leaking. Yes, we also need to destroy the VM when we return. We also need to destroy the module when we return. We also need to destroy we don't need to destroy the program because we're doing execute one shot. This will automatically destroy the program, but we're leaking a couple of things. I'm not too worried about that at the moment, because, well, when we are done with the program, like the memory is going to be freed anyway. But this is certainly something that we need to fix. There are also a couple of more issues at hand. For example, let's call this one main2. And then we have a segmentation fault, because we're trying to find a name function, but this doesn't work. There isn't one. So let's handle this case more gracefully. Program does not contain main. And another issue, this can't happen at the moment, but the signature could be wrong. So it could be called main, but it might take more arguments than we're expecting. We're currently only handling the case where it doesn't take any arguments. So let's get the signature as well. Function signature of the main function, and sig.input count Angular. The output count isn't 1. Signature Perfect. Okay, program does not contain. So now we're handling those bottom conditions a bit more gracefully. Yeah, like that. So. Okay. This is basically everything that I set out to do during this stream. So are there any questions? Okay. Otherwise, thank you for stepping by. I will do this again soon, and then we will start actually putting stuff in our function bodies and do a bit more things. Thank you.